Back to max-min fairness. This definition might be a little complicated, but one way to look at it is to say, if I have a given allocation, I try to improve it by doing a move that would improve fairness. So you are Robin Hood, you try to take from the rich to give to the poor. If you can't do that, you should do it, and you do it. And then you do a number of moves. After doing that a number of times, you come to an allocation where you cannot do that anymore. You cannot do that because you're in that situation. Whenever you try to give to someone, you have to take to the poor. So you cannot take from the rich. So once you have reached that state, that stationary point, if you want, of your iterative algorithm, you have reached what we call a max-min fair allocation. So you cannot play the Robin Hood game and take from the rich to give to the poor. That's an axiomatic definition of max-min fairness. The good news is that it always exists, at least if we can express the constraints posed by a network as a set of convex, translate that into a convex set. But even better than that, instead of checking for whether a given allocation is max-min fair, we have a very simple constructive algorithm, which is called progressive filling or water filling, which is the following. Consists in saying, I will have a given network. I will apply the following. I mark all sources as non-frozen. Then, a number of steps. At every iteration here, I will increase synchronously the rates of all the sources that can be increased, that are not frozen. By doing that, of course, I may hit some of the capacity limits of some of the links. When I do that, I observe which flows are using those capacity limits, which flows are using the resources that hit the limit. Those flows, I freeze them. I declare them as frozen. I will not increase them anymore. And then I come back. At every iteration, I will hit at least one of the capacity limits. So I will freeze at least one of the flows. So at every iteration, I will reduce the number of non-frozen steps. If I have a finite number of sources, it must stop. So this algorithm will terminate and will provide a given allocation. Well, there's a theorem that says that this algorithm exactly produces the only max-min fair allocation. So another way to view the max-min fair allocation, instead of saying this axiomatic Robin Hood game, we can say, well, this is the result of this water filling algorithm, which is less axiomatic, so that's why we see the other one. But let's see how it works on this example. We know what is the max-min fair allocation. That was the previous poll. Now let's see what this algorithm does. We have the 11 sources. We try to give the same rate to all and increase it. Increase it as much as we can. That means we're solving an optimization problem where we give a rate t to all sources and we maximize the rate t. At the end, we obtain 1. That's the egalitarian allocation that we have discussed an hour ago. But that's only the first step. We try to give as much as possible to everyone. We obtain 1. Now, when we obtain 1, why did we have to stop? We had to stop because of capacity of the second link, where we had 10 sources that hit the limit. So all of those 10 sources are now frozen, the green and the red. But the blue is not frozen, so second round of the algorithm, I increase the blue as much as I can. So I have again a maximization problem, maximize t, such that the constraints are satisfied. The constraints are only the constraint on x1. x1 should be feasible, so x1 should be equal to t, such that t plus 1 is less than 10. T plus 1, because the red x0 is frozen equal to 1. So the max is easy to obtain, it's 9. And then once we've done that, we hit the limit of the first link, which forces us to freeze also the blue source. Then everybody is frozen and the algorithm has completed. And what we have at the end is indeed the max-min fair allocation. Well, voila. This is one way we could think of allocating rates in the internet. Well, to check your understanding, here is a variant. What is the max-min fair allocation in this example? Yes?
345,
3C. That's a good question. It should be 4, yes. More seconds. That's not my fault. I really clicked only once. Okay, click again. That's faster the second time. Right. And the correct answer is the majority ones. It would have been a pity to not have the feedback. How did you compute it? Well, I'm proposing here n different allocations. For each of them, you can test whether it's max-min fair, or you can simply compute the max-min fair allocation, because that's always easy. It's a simple algorithm. If we do that here, then we simply give the same value to all, and then the algorithm converges in one step, which is exceptional. It's just because it's a very simple, symmetric academic example. So we give the max t to everyone, we obtain c over 2, and when we do that, at the same time, all the constraints are satisfied with equality. So we have to stop everyone. So this is what fairness would give here, and we could stop there and say, well, we have an understanding of what fairness should be, but not quite. And I use this example to illustrate the criticism that some people brought to max-min fairness. So max-min fairness is used to allocate rates, for example, in metropolitan area networks with ADSL and systems of that kind that will tend to allocate the available capacity over the ADSL network using the concept of max-min fairness. But some people in academia, you always find somebody who can find a good argument, said, well, but if you look at what we're doing here, we give to the C, the red, exactly the same as the blue. Right? Which was desired in some sense, because we said, if we want to maximize the throughput in this network, what would we do? Yes?
And I think we should give the same rate for all link.
Yes.
Like C over 5, since there is 5 link.
Mm-hmm.
So everybody has the same. And then if we can add some more resource to one link, we could add some. But it's not the same.
Okay, so you are perhaps the person who issued that that concern here. So exactly this one. So you said you would like to give perhaps not the same to the red as the blue, because the red are using 4 times more. So perhaps they should receive 4 times less. Some kind of proportional accounting for the resources that you use. This is exactly the criticism that some people made to max-min fairness. And there is now a second form of fairness, which is proportional fairness, which is trying to capture exactly this. So proportional fairness has been invented after max-min fairness. and as we will see, both are somehow relevant to the internet, where we say, well, of course, we need to be better than simply maximizing the total utility, but instead of being as strictly fair as max-min fairness, let's try to apportion the use of resources to the rate we get. If I'm doing a flow that's very long, that uses the entire internet, perhaps it's okay if I receive less than somebody who goes next door, right? There is some fairness to that statement. So formally, one way to define it is the following here. It consists, again, the same game. I have an allocation, X, and I'm trying to move it, Robin Hood, making it fairer. And if I reach a state where I cannot move, then I say it is proportionally fair. Now, what are the allowed moves? Well, we say that I cannot move if any change that I will do would have a balance which is negative, where the balance now is the sum of the relative changes. So I have a given allocation X. I try to move and go to Y. If I move to Y, some rates will increase, some rates will decrease. So there is a delta, which is ys minus xs. If I take the relative change, that's the delta x divided by x, that is how much in percentage people have lost or won. And then I do the balance of that. Some people have lost by 1%, other people have gained 10%. If the balance of that is positive, I should do the move, right? If the balance is negative, then it's not bad, I should not do it. So we say that as long as the balance is positive, I'm allowed to do moves and I'm improving the fairness. What's the idea behind? Well, if you have, say, a single resource, let's say one link at 10 megabit per second, and I have one source that's getting 0.1 megabit per second and the other is getting 9.9. Now, if I do a move, if I add 0.1 to the first, the delta for this guy is plus 100%. I've doubled, right? The loss for the second is from 9.9 to 9.8, so it's an epsilon, it's 1%. Something. So the balance of that is plus 100% minus 1%. So should I move if I increase u by 100% and I decrease u by 1%? The answer here is yes, I should do that, because if I weight the two, you gain much, much less, more than what I take from you. So Robin Hood say, let's do it. So we do that iteratively. At the end, if we reach a point where we cannot do it, any move that I do from this point would have a negative balance. If that happens, negative or zero balance. That means I've reached a stationary point, I cannot improve it, and if I find such a point, I call it proportionally fair. We call it proportionally because here we care about the proportion, how much in relative value we increase or decrease someone. That is the idea behind. Now it has two effects. First, what matters are the relative values, and second, also because we take the sum of all we take the balance, the total balance, we somehow account for the global effect, which intuitively should have this desired property. If one person has a very large effect on the network because it's using all the routers in the world with one multicast flow, for example, then a small change to this guy might give a lot of positive change to everyone. So it accounts for the global usage that we're making of the resources. This is why it was proposed. So if we look at this example, here are two possible allocations. For the first one, the one we've seen before, which was the max-min fair allocation, and for the second one, it's also the max-min fair allocation. Are they proportionally fair? close the poll and hope I get it right. Yes. And the correct answer is none, which is perhaps far from obvious. Let's see why. Let's look at the first allocation. Well, this one we expect that it is not proportionally fair because this is what motivated us to introduce proportional fairness. Let's check that. We give the same to the red and the blue. Now, intuitively, I should be able to decrease the red while making the blue happier, and the balance should be positive. And this is possible because the red counts 4 times. Right? So if I add a small delta to the blue, and I remove this delta from the red, so that I keep all the links saturated, let's do what is the balance. Well, the balance is this one. I have removed 1 delta from the red, and I have 4 times increased delta of the blue. So 1 that I take away from the red, I was able to give it to 4 people. So if I look at this way of computing the balance is positive, so I should do it. I should take away from the red to give to the blue. So it's not proportionally fair. The other is the same. I can also increase the blue a bit by and the x2, which is the green, and reduce the red for the same argument. The red is increasing more resources. If we do the math, we find that for delta small enough, then because a little bit we take away from the red, we're able to give it to 9 greens and 1 blue. So the balance again will be positive, so we should do it. It's not the proportionally fair allocation if one exists. Now, same question as before. Well, we've defined this axiomatically. Now, does it work in practice? The answer is yes. Under the same conditions as max-min fairness, proportionally fair allocation exists and is unique. And we can compute it also. It's a bit more complicated, but it's intuitively very simple to understand. The proportionally fair allocation is maximizing not the sum of the rates, like the maximally efficient allocation, but the sum of the logarithms of the rates. Now, why the logarithms of the rate? Well, because logarithms has the property that the derivative is 1 over x. So if I want to maximize the log, I will move to a point where the gradient is 0, and the gradient is 0 means that quantity is 0. And that quantity is the relative changes, which is the sum of delta x over x that we had as criterion for max-min fairness. So the log function in particular is concave. That means if I increase from 10 to 1, the increase in log is much smaller than if I increase from 1 to 2, for example, which is exactly what we mean by being proportionally fair. So that is our second important theorem of the day. For max-min fairness, the algorithm is, it exists and is unique and is obtained by water filling. Proportionally fairness exists and is unique and is obtained by maximizing the sum of the log. That's a convex maximization problem, so it is in practice doable. Let's do it for this example. We have 1 red, 4 blues. The red uses 4 hops, the blues use 1 each. Then if an omniscient observer wants to compute what should be the proportionally fair allocation, he has to solve this maximization problem. Maximize log x0 plus log x1, etc., subject to those 4 constraints. So you ask MATLAB fmin search or convex programming to compute it, or because there's a lot of symmetry here, we can find a direct solution. A direct solution can be found here because if we analyze those constraints, we see that they are linked only via x0. So if I look at one of those constraints, if I have a given value of x0, then I can always increase x4 because x4 does not appear in any of the other constraints. So if I have a given allocation that has a given value of x0, if I want to be maximally efficient, if I want to maximize the log, which is an increasing function of x, I should have equality here. Because if I don't have equality, then x4 can be improved, can be increased. The same is true for all. So once we know x0 of a given allocation, if we want this allocation to have a chance of being the proportionally fair allocation, there must be equality in each of the conditions. This is quite special. Usually in convex programming, you don't expect to have equality in all of the inequalities. Otherwise, that would be too easy. But here it's true. So we have equality everywhere. So that means there is some quantity x star such that we have equality everywhere. So the problem reduces to a 1D problem with one single variable, x0, that I can now solve. I have to solve maximize u, which is log x star. X star is x0. Plus the sum of the rates of the others, which are all equal to c minus x star. So I have now a high school problem, maximize a function of one variable, x star, which is given by this, subject to the constraint x star between 0 and c. So I study this function of x star by computing its derivative, and that finds that it has a maximum. Well, we know from the theorem there's a unique maximum anyhow, so we can try to compute the derivative. We find this, we set it to 0, and at the end of this long story, we find x star is equal to c over 5, which was your proposal, right? So essentially, the intuition of proportional fairness here is fair. It's saying we should give the same to everyone, but accounting for the fact that the red should be counted like using 4 times as much as a blue. And therefore, we get that the blue get 4 times as much as the red, because this is using 4 times as much, so it pays 4 times more. So that there is, in some sense, fairness. So this is the proportionally fair allocation for this network here, 1 over 5 for the red and 80%, 4 times as much for each of the blue. We should expect that the proportionally fair allocation gives less to the red than the max min fair allocation. That's exactly the intuition, and we can check it here. The max min fair allocation gave the same, which was 50% of the capacity to each of those groups of variables. Now it gives less to this one. So check your understanding. Here I propose 4 possible solutions. I don't ask you to compute the solution, but by elimination, which is the only possible one. So you have to trust me that one of those 4 is the correct solution. Which one is the proportionally fair allocation? So I stress there is no computation to do, just qualitative reasoning. Except if you have a wired-in convex optimizer, which you can also use.
Il devrait avoir déjà x2, il devrait avoir plutôt plus que x2. D'accord. C'est x2 et x0. D'accord. x2 il a c'est x2 il a
5 more seconds.
Xf dus nu je kunt doen.
And this is the correct answer. Let's see why. Well, one is the proportionally fair allocation. Is not proportionally fair. We've seen that a minute ago. That is the max mean fair allocation. Now we expect that the proportionally fair allocation will give less to the red than the max mean fair allocation because the red is using more resources. So that eliminates solution 3. Solution 3 is certainly not the good one. Now it could be 2, but 2 is also not a good solution because if we look at x1 plus x0 is less than the capacity. So I can increase x1. I can start from this allocation. I can increase x1 without stealing from anybody, by the way. I can increase x1 alone because there is slack in the system. So I can do the game of Robin Hood, so I'm not stopped, it's not proportionally fair. In mathematical terms, people say that the proportionally fair allocation is what we call Pareto efficient, in the sense that we cannot increase it. We hit the limit somewhere. It's more than Pareto efficient. We cannot increase it without violating the game of global balance being negative, but an allocation that is not Pareto efficient, that like number 2, not Pareto efficient means we can improve unilaterally one of the resources. Yes?
But number 4 is not exactly saturated. If we multiple by x0 and x2 should be 10 exactly.
Yes, so thank you. You're in computer science, right? Yeah. So formally I should have written an infinite sequence of 0, 1. Yeah. x2 is 1, 0, 1, 0, 1, 0, 1, 0, 1, etc. Infinite periodic. Yeah. So it's a multiple of 1 over 9. So if somebody tells you modulo the accuracy of the floating points number that are given here, that one of the solution is the proportionally fair, it can be only 4. 2 is not Pareto efficient. It can be improved by unilaterally increasing one of the sources. 3 goes in the wrong direction, so there's only 4. But you're right. The correct solution is, it's not 1 over 9, but 1 over 11 is obtained by exactly the same method we had seen before, which is computationally not instantaneous. We do the same maths, and we find exactly 10 over 11. Voilà. We have seen 2 forms of fairness. That's the embarrassing part of the story, but this is how things are in the internet. We'll see that the internet is somewhere in between. It's between max mean fairness and proportional fairness. But what exactly it's doing is harder to understand, therefore we see the 2 simple things. And to understand better what the internet is doing is useful to interpret proportional fairness in the light of the theorem that says proportional fairness is the same as maximizing the sum of the logs of the rate. Well, we can consider the log of the rate as a utility. So assume there is a social welfare provider, an optimizer, a planner, that decides the utility can be measured and is the log of your rate. And now I want to make society happy, so I maximize the sum of the utilities of everyone. If I do this, I'm implementing proportional fairness. Now if instead, then we can argue, but is log really the good function? Why not square root? Why not whatever function? Some people have studied that, Walrond and Moe, and they found that if we take a class of functions, like those red functions here, which are, here's the log. The log is a concave function. Concave means the derivative decreases as x increases. The slope decreases. The slope is the increment by how much I increase the utility by adding 1 to the rate. If I have a large rate, I don't increase much. If I have already 10 gigabit per second, receiving 10 gigabit per second plus 1 kilobit is completely negligible for me. If I have 1 kilobit per second, receiving 1 more doubles, and I'm much more happy with 2 than with 1. That's what this captures. But other functions that are concave also capture it. If we take concave functions that are close to a step function. In the limit of that, for each of those red functions, we obtain a rate and allocation that is called utility fair. We maximize some arbitrary utility function. In the limit of the red function becoming a step function, we obtain something which is exactly the max-min fair allocation. So the max-min fair allocation is not a utility function. We can obtain it as simply maximizing a function. Otherwise, I would have given it this way because it's easier. We have to do this complicated axiomatic thing to understand what it is. But we can reason about it as if it would be maximizing a utility function that has a knee here, that has a very strong curvature at one point when we're close to 1. So remember this, because when we will see TCP, we will use that again. So at this stage, let's recap what we have seen. Well, we have seen that if we run a network, then it's not okay to let everybody whatever they want, because we take the risk of congestion collapse. By the way, it happened in the internet in 1985. TCP did not, there was no congestion control in the internet, and then there was a congestion collapse where all sources were trying to send and the total throughput was very, very small. And then congestion control was put into the internet that we see now. So we need to do something which is called congestion control. And I've seen that in order to do that, we have to maximize something which is fairness in some sense. We have to implement some form of fairness, which can be, depending on taste, max-min or proportional fairness. Well, that's what we should do. Now, how can we do it? People in the past have implemented a number of things, but today in the internet exist 3 ways to implement fairness, depending on the situation. The top 2 ones are special things that exist only in small-scale network. Essentially, the top one says, well, let me be the oracle, the omniscient social planner that knows what the rates should be, and I give the rates to each of the flows. That's what you do, for example, in smart grids when you have streamings of data and you have rates that need to be allocated to all your devices so that they get exactly what they want. So you control the rates, and then you make sure that the links everywhere satisfy the rate constraints so that there would be 0 loss. That's one way to do. It works in a controlled environment, in a network where you control everything. You control the rates, you control the links, and you control who comes into the network. So typically in small-scale industrial networks. In the internet, we don't do that. There is not somebody coming to my PC to say, now send at 0.5 kilobit per second, because on the transatlantic link that you're using, there's 1 million other flows competing with them, and I've told each of those 1 million flows to also use max 0.5 kilobit per second. That would not work in the internet. So we use something else, which is called end-to-end congestion control, where we have an adaptive algorithm in the hosts to test the water and see how much we can send. This is what we will see now. There's also something intermediate, which is sometimes used in some local area networks, which is called a back pressure signal, but is very much used also inside computers, so in closed environments, where, for example, when a processor sends traffic to a memory, then it will, if the memory is, if there is a problem on the bus of the computer, then there is a stop or go signal, which is in the case of a computer, physical state of a given wire on the bus. In a local area network, sometimes you can implement explicit messages that come from switches that send back to the sources a stop signal. It's not very much implemented, so we will not discuss it in the internet. The major thing that we need to understand is end-to-end control. End-to-end control can be done in any form, but in the internet we use practically exclusively what is called additive increase, multiplicative decrease. So let's understand now what this is. So it is a way of controlling the sources such that eventually all the rates that the sources use are satisfying something like proportional fairness. That's the ultimate goal. We'll see that in several steps. When people invented this, they said, well, let's do some kind of control that is linear with respect to this model. So we start with a simpler network model where I assume I have a single resource with a single capacity. That's sometimes how people think about networks, but of course this is too simple, and we'll remove that restriction limit in a few slides. But this explains how and why we use additive increase, multiplicative decrease. I assume that I want to design a control for the sources, so at every time t, source I sends with the given rate xi of t. Then n sources use the link that has a capacity c, and then at every time slot, periodically, every round trip time, for example, I send a signal back to the source, which is y of t. And the assumption here is that the signal is the same to all the sources. That's one of the key assumptions that makes the system scalable and apply to the internet. So if there is one link, there is one signal. And if there's 1 million sources using that link, each of them will read the same signal. We will see in the internet that this signal is in fact the loss of a packet. For the time being, let's assume we have an academic exercise where we simply receive a signal which is 1 bit, 0 or 1. And then the rule of the game is the sources are allowed to do the following. If the signal 0 means there is no congestion, and 1 means there is congestion. And then the rule of the game is if we receive y equal 1, then at the next time slot, everybody will reduce their rate. Otherwise, we will increase. And we look at only linear laws, which gives us increase or decrease laws of that type. Whenever I receive negative feedback, y equal 1, then I increase linearly, so I apply a linear function, affine in fact, with a linear component plus some offset. I say the new value of the rates that I am using, I am source I, is the previous value multiplied by a number u1 plus v1. And if y is equal to 0, same form, but of course with different parameters. The question now is what are the good value of u1 and v1? Well, we see that obviously when y equal 1, that means when we receive negative feedback, then we should decrease, which means that the u parameter, which is the factor, should be 1 or less. And the v1, which is the additive term, should be in fact a negative term, should be a decrement. And similarly, u0 should be larger than 1 and v0 larger than 0. Right? So this is all obvious stuff. Here is an example of a simulation of a scheme like this with u1 equals 0.5, v1 equals 0, u0 equals 0, v0 equals 1. That means when I receive negative feedback, I divide the rate by 50%. New rate becomes 0.5 old rate. When I receive positive feedback, I increase the rate by 1. New rate becomes old rate plus 1. This is additive increase, multiplicative decrease. I'm simulating what happens on a network that starts with 2 sources. I'm showing the rate of source 1, the rate of source 2, and then the third source is that starts at time 100. And we see when the source starts at time 100, then there's an impact on the 2 sources. And we see that this algorithm does not converge, but it oscillates around value that are more or less the capacity. Here is the total rate. The total capacity is 10. Of course, the rate will exceed because the only way to give negative feedback is to exceed the rate. Yes?
Shouldn't u0 be equal to 1? u0.
No. The u0 equal 1, sorry, is equal 1. Yes, sorry. Thank you. The next question is, well, here is an example. What in general would be the best way to choose u0, u1, v0, and v1? Well, to understand that, it's important to be able to understand this diagram here. Here I'm focusing on two sources. So I have a small network with only two sources. I'm plotting on the x-axis the rate of the first, on the second axis the rate of the second, and I'm showing a possible iteration of the algorithm. I start from x1, x2, that gives me this point. Now what happens if when I receive a new rate, then I move here, as soon as I receive positive feedback, so the capacity is not exceeded. It's only when I hit the capacity when I go beyond this line here, then I will decrease. And where should I target going? Well, I should be fair. Now, proportionally fair or max mean fair. Which one should I choose? Well, in this scenario where I have only a single resource, proportional fairness and max mean fairness are the same. Because if we do water filling with max mean fairness, we get the same rate to everyone, C divided by 2. And with proportionally fairness, it's easy to see we will get the same as well. If we give less to one, then we should steal from that to give to the other. If there's only one resource, then that's what we should do. So there's no complex definition of fairness in that case, which means we should target the diagonal term here, which is the red circle thing. So we should find the coefficients u such that we move towards this field, towards that point here. To understand what happens, can you qualify? Here I've illustrated two possible choices of the coefficients u and v, the blue and the green, A and B. A, and I'm saying one of them is additive increase one of the moves corresponds to additive increase, one of the moves correspond to multiplicative increase. Which one? So that's an easy one. I close in 5 seconds. Well, well, the correct solution is the majority vote. Why? Well, when we do additive increase, what we do, we add to the vector v a constant vector, which is by how much we offset the rate, v0. So by doing that, it's a move which is parallel to the diagonal. That's the blue. When we do multiplicative decrease, that's we multiply the vector by a constant term, we give the green move here. Okay. Now, if we want to have an algorithm that will move towards fairness, which one is better, the blue or the green? Additive increase or multiplicative increase? Assume now through randomness we receive sometimes positive feedback, sometimes negative feedback, so we will move. Sometimes we will do decrease, sometimes we will do increase. If I do an additive increase move, an A move, rather than a B move, do I improve fairness? Yes. So I get, in relative terms at least, I tend to get closer to the diagonal. When I use the green move, I stay where I am. I don't make things worse, but I don't make them better. Well, that's the major argument. If I do additive increase, it's better than multiplicative increase. And if I do additive decrease, it's really bad because I'm going away from fairness. So what I should do is certainly never do additive decrease, but I have to do some decrease once in a while, so I should do multiplicative decrease. And for the increase, well, I can do perhaps a combination of multiplicative and additive, but there must be an additive increase term. So the only element of this algorithm that improves the fairness is the additive increase. So we must do additive increase and certainly not additive decrease. Therefore, in the internet, we use, among such controls, which was the boundary conditions that were put on the design of the internet congestion control, then we have to use additive increase, multiplicative decrease. That's the only combination that's worked. Voilà, that's the end for today. See you tomorrow at 11:15 with your clickers.